In part 3 of this lecture, we are going to continue with the properties of Laplace transform. Next properties is the integration. Okay. So integration states that if we have a signals of ft in time domain, which is said to be integrated. Okay, so we have f tau d tau, in which the integration is from 0 to t. The Laplace transform of this integrated signal is equals to fs divided by s. Okay, so let's have a look at this example for the integration properties. So we are given these equations where we have 2at, okay, plus 3 plus 1 over 1 divided by 0.1. Integration of 0 to t of ax dx equals to 4 exponential negative t of ut. So we are requested to find the at. So in order for us to solve for these questions, we have to first transform this equation into a Laplace transform. So let's have a look at the solution of this example. So this is the questions, right? So we're going to transform all of the terms here into a Laplace transform. So we are supposed to get 2 of as, okay, plus 3 over s. Okay, so 3 is considered to be a step function, 3ut. So 3ut, if we transform into Laplace, we're going to have 3 over s. Okay, then this is to be used. This is to be based on the integration properties. So when we have the integration term, so the Laplace transform will be simply 1 over s, or as over s, yeah, as divided by s. Okay, this is to be based on a Laplace transform. Okay, all right, so I think I made a mistake here. Supposedly we have 1 over 0.1. It's supposed to be 10 over s. I think I made a mistake here. You need to correct this for me. I'm very sorry. Yeah, it's supposed to be 10 as divided by s. Yeah, 10 as divided by s, not 1 over 10. Yeah, so just to correct this, we're going to have 10 multiply with as divided by s. Yeah, so please correct this for me. And for the right hand side is supposed to be 4 over s plus 1. So this is to be based on the frequency shifting properties. All right. So since there is a correction on this particular terms, okay, so you're supposed to get as or 10 of as divided by s. So the rest of the solution is wrong actually. Yeah. So please correct this for me. So this is totally wrong. But I believe that from what we have learned from the previous part of this lecture 14, which is the properties of Laplace transform, I believe that you can solve for the final solution. Yeah, you can find the final solution for these questions. Yeah, so please, it's my mistakes. Yeah, it's my mistakes. It's supposed to be 10, should be located here. Yeah, 10 of as divided by s. Yeah. Okay. All right. So the solutions that I made here is wrong. This is the case where I assume that this is 1 over 10. Yeah, so it's my mistake. Sorry for that again. Okay. So let's continue with the lecture. Yeah. Okay. So this is the examples here, which is basically the examples that I give you here is to use a partial fraction. Yeah, partial fraction to solve for the yt. Okay, so I'm not going to do this. Yeah, the example I'm not going to do this. I believe that you can try to solve this on your own. Yeah, a and b is basically to use the partial fractions. Yeah, find the partial fractions, and then from the partial fractions value, you can find the inverse of Laplace transform. And the second question here is to be based on differential properties. Yeah, so we did this example in the previous slide, so I'm not going to do this. So you can do this on your own. Try to solve this problem on your own. Okay, so if you got a problem with this, you can just contact me. Yeah. Okay. So this is the last two properties to be learned in this lecture 14, which is the initial value theorem and the final value theorem. So what is meant by initial value theorem and final value theorem? Okay, so for initial value theorem, basically you can find the initial value of time domain function. Okay, if we look at these equations here, limit of t approaching 0 positive or t equal to t approaching 0 of ft. Okay, this is meant by f0, initial value, yeah, t0, t equals to 0 is the initial value. Okay, so to find the value of f0, yeah, value of f0, the initial value, it is actually equals to the limit of s approaching infinite of s multiplied with the fs. Okay, right. Whereas for the final value theorem, which is the final value of ft, in this case, you assume that the final value is f of infinite, yeah, f infinite. So it is equals to the limit of s approaching 0 of s multiplied with fs. Okay, so it is quite maybe it's good to explain about this theorem using the examples, yeah. So let's have a look at the examples which can be used to make us more familiar with this theorem, yeah. Okay, let's have a look at the example here, which is to we are given the xs, yeah, we are given the xs, which is equals to these terms, yeah. So the question now is to obtain the initial and final value for the time domain signal, which is the xt, yeah, using the initial value and the final value theorem. Okay, so if we are given the xs, the Laplace transform of the xt, we can find the initial value in time for time domain, which is x0, and also final value, which is x infinite, by applying the initial and final value theorem. Okay, so how to find this, the initial and final value for xt? Okay, so let's have a look at the solutions here. Okay, so this is your xs that's given the questions. So by using the initial value theorem, we know that from the slide just now, the limit of t approaching 0 of xt. Okay, now I simply use x0. That is, when the limit t approaching 0 of xt, this is also equals to x0, right? So x0 can be calculated by calculating the limit of s approaching infinite of s of xs. Okay, I'm going back to the lectures. Okay, this is the one. Yeah, the limit of t approaching 0 of ft, which is f0, is equal to the limit of s approaching infinite of s of fs. So this is what this is what I adopted in solving the initial value theorem for that. Yeah. Okay. So we have the limit of s approaching infinite of s, and the xs is this. So I just substituting all of this xs into here. Okay, so I'm going to find out what should be the limit of s approaching infinite for the s multiplied with the xs. Okay, so for this, what I did is I'm taking out the s squared from the numerator. So we have x power of 3. We have 2 plus 5 over s plus 5 over s squared. And for the denominator, what I did is I take out s power of 3 and left with these terms here, 1 plus 2 over s plus 10 over s squared, and here we're going to have 1 plus 2 over s. So this one can be cancelled out. So when we substitute the limit of s approaching infinite to these terms, end up we're going to get that the value of x0 is actually equals to 2. Okay, right. So it means that we can find the initial value for the time domain signal by applying the initial value theorem, which is simply the limit of s approaching infinite of s of xs. So by calculating this limit, we can then find the initial value. So the same things apply if you want to find the final value for the xt, which is x infinite in this case. So what we did is we just apply the limit of s approaching 0 of s of xs. Yeah. So when we're calculating this limit of s approaching 0 of this particular term, it can be verified, it can be proved that the value of x infinite will be equals to 0. Okay, you can try this, yeah? Okay, you can prove this by simply substituting the value of s equals to 0 in the equations here. So that will give you 0, which means that the final value for xt is 0, yeah? Okay, hopefully you understand about this initial and finality theorem. Okay, so that should be the end of properties of Laplace transform. So let's have a look on the examples examples that are related to the properties of Laplace transform. Yeah. Okay, so we are given this example. We have two signals xt and yt, where xt is equals to t of ut, it's a ramp function, yeah, t of ut, while the yt is the exponential terms, decaying exponential negative 5t of ut. Okay. So from these two signals given, xt and yt, you need to calculate, you need to find the Laplace transform for zt. So there are two zt's given here. The first zt is xt plus yt. Okay. And the second zt is x2t minus 1. So we need to find the Laplace transform for both zt, yeah? So let us try to solve for these examples. Okay, so these are the signals given, xt and yt. Okay, for the first question, we have zt is xt plus yt. So xt is 2ut, while yt is exponential negative 5t of ut. Okay, so by applying the properties of Laplace transform, okay, so we are going to use these two signals here. The first one is signal number 5, which is tut, by substituting n equals to 1. And the next one is signal number 6, which is exponential negative 80 of ut. So based on that, we are going to get that the Laplace transform for zt, which is zs supposed to be 1 over s squared plus, which is based on the derivative properties, 1 over s plus 5. So it's straightforward, yeah? The second example, which is to find zt equals to x of 2t minus 1. So this is a case whereby the xt is said to experience time shifting and time scaling. Okay, so what we did is that always proceed with the time shifting first. So we know that for the xt itself, which is a ramp function of tut, the Laplace transform for xt will be 1 over s squared. Yeah. So if xt is said to experience a time shifting of 1, so the results for the Laplace transform will be 1 over s squared exponential of negative s. You can refer to the time shifting properties. And subsequently, when we consider the inclusion of time scaling, x2t minus 1, the Laplace transform is simply 1 over 2, okay, multiply with 1 over s over 2 squared, exponential of negative s over 2, okay. So you can refer to the scaling properties to obtain these results, yeah. So this is the answer for the Laplace transform for the xt, which experience the time shifting and time scaling. Right. So let's have a look at this part B of the questions. Need to solve a differential equation below using Laplace transform method. Yeah, so the initial condition is v0 equals to negative 5. Okay. Right, so we are given the differential equation is v prime or dv over dt minus 2v equals to exponential of 3t. So we need to find the vt, yeah? Need to find the vt. So let's have a look at the solution for this example. So we have this. Okay, so what we did is we do the Laplace transform. So for the first term, which is v prime dv over dt, Laplace transform will be s over vs, svs minus v0. So this is to be based on differential properties of Laplace transform. Okay, minus, so 2v will be 2 of vs, while the third term's exponential of 3t will give us 1 over s minus 3. Okay, so this is the the Laplace transform for this time domain signals or time domain equations. Yeah. Okay, so we're going to substitute the V0 given in the question. V0 is -5, so I'm going to substitute in this equation. So end up, we're going to have these terms here. Okay, Vs, S minus 2, sorry, this is S, yeah, not 5, yeah. S minus 2, and 5 should be there, equals to 1 over S minus 3. This is S, yeah. Sorry, my handwriting is quite confusing. Sorry for that. Yeah, 5 and S is about the same. Okay, S minus 2 plus 5 equals to 1 over S minus 3. So Bs will be then equals to these terms here. Okay, and when we try to solve for that, we're going to have 16 minus 5s over S minus 3 multiplied with S minus 2. Okay, so this is your Vs. So what you have to do, instead you have to use a partial fraction to find for the Vs in partial fraction terms. And once you have the partial fraction terms, you can use the inverse of Laplace transform to find the Vt. So I don't have to find the Vt for you. So I believe that from this step, you can proceed further with the partial fraction and you do the inverse Laplace transform to find the Vt. Yeah, you can do this on your own. Okay, I hope it's clear on these examples. Okay, let us proceed with these examples here. We are given two signals still. We have Wt. Okay, Wt is basically a ramp function having a slope of 3. And then we have given the Yt, okay, in this particular form, right? The signals is extended from 0 to infinite. Okay, the same things happen for Wt, extended from 0 to infinite. Okay, so Wt and Yt are used in this figure question 2b, where Wt is the input to the system. Yeah, Wt is delayed by 3 seconds, which produce the x1t. X1t is multiplied with the Yt, okay, and the multiplication yield is x to t, and the x to t will be then input to the integration box and will give us zt. Okay, so this is a system that is created based on the input of Wt and Yt. So from these questions or from this diagram, we are requested to number 1, write the equation for signal Wt and Yt in the form of step unit. Okay, so this is basically things that we have learned in chapter 1. Yeah, so let us find Wt and Yt in the form of step unit. Okay, so we know that from the diagram, Wt can be simply written to be 3t of ut because the slope is 3. Yeah. Okay, for the Yt case, I believe that you can just please bear with me in solution for the Yt. Okay, so we're going to have for Yt, there are three portions. Yeah, so I'm going to do it one by one. The portion number 1 is from 0 to 1. Portion number 2 is from 1 to 2, and portion number 3 is from 2 to infinite. Okay, that's why the solutions for Yt is written into 3 different terms here. So this is the first portion, which is between 0 and 1. So 0 and 1, the equation will be 2t, yeah, because we have a ramp there with a slope of 2. And the limit is from 0 to 1, so it's written to be ut minus 1. So this is portion number 2, which is a constant of 4. And the constant is having a range from 1 to 2. So we have 4. And the constant from 1 to 2 is written in terms of step function, which is ut minus 1 minus ut minus 2. And the third portion, which is a constant to infinite, this is 2 of ut minus 2. Okay, so we are now going to rearrange the equations here, the terms here. So we have 2t ut minus 2t ut minus 1. This is for the first term. Second term is 4 ut minus 1 minus 4 ut minus 2 plus 2 ut minus 2. Yeah. So I'm going to rearrange again. So 2t ut. Okay, so this is a combination of the second terms and the third terms. So why I combine these two terms here? Because they are having same terms of step, which is ut minus 1. So I'm going to combine them together. Yeah. So the fourth terms and the fifth terms are added together. So we have -2 of ut minus 2. Okay, so further on, we're going to have 2t ut. And for the second terms, we can rewrite this as -2. I'm taking out the 2 value. So 2 or -2. And the inner side will be t minus 2 multiplied with ut minus 1. And the third term is here. Okay, so please be careful with the second terms here. Okay, these equations will be meaningful. Yeah, will be meaningful if the RAM shifting constant, yeah, the RAM shifting constant, and the step function shifting constant, yeah, shifting constants are the same. So that will be useful. Yeah, I repeat it again. The RAM shifting constant and the step function shifting constant should be having the same value. So that is why for the second terms here, I'm rewrite the terms to be t minus 1 minus 1. Okay, t minus 1 minus 1 is similar to t minus 2. So the reason why I did this is that I want to find out, I want to make the constant for the RAM and the constant for the step to be similar. Okay, so from here, I can separate these terms here. So I can then take out t minus 1 and ut minus 1 to be the second terms. And then I'm taking out -1. Yeah, I'm taking out -1. So we have -1 times -2 will be +2 of ut minus 1. Okay, so from the second terms here, it is then separated into second terms and the third terms. So there are two terms here. The first term here is a RAM, yeah, with a step, and the third term is a step. Okay, so hopefully you understand about the process here. Okay, so we have yt is written to be in this 4 terms value. Yeah. Okay, so this is the answer for part A. For part B, number 2 is to determine the Laplace transform for Wt and Yt. Okay, so from the Yt and Wt and Yt that we have calculated or obtained in the first part, we have to obtain the Laplace transform for both. Yeah. So let's have a look here. Wt is 3t of ut. So straightforward. Ws will be 3 over s squared. Yeah, you can refer to the table. And for yt, the Laplace transform will be ys. The first term will be 2 over s squared. Okay, the second term, okay, this is a case whereby the TUT is shifted by 1 unit. So we have to deal with the shifting properties. So it's going to give us 2 over s squared exponential of -s, yeah? The shifting properties. The same things applied for the third terms. The shifting properties are shifting by 1. So that will be 2 over s exponential -s. And for the fourth term, it will give us 2 over s exponential -2s. So this is the Laplace transform for the ys, yeah? Okay, and number three, you have to find the approximation of zt in the s domain. Okay, so you will need to find the zt here. Okay, so you have to calculate it, or you have to use all the given operations. Yeah, you have to use all the operations given in this figure to find the zt. Okay, so let's have a look here. X1t will be a delay of Wt by 3 seconds. The X1t, which is a delayed version of Wt, will be multiplied with Yt to give us the X2t. Okay, let us find the X2t first from this operation, yeah? Okay, so from the figure, we're given that X1t is Wt minus 3. So that will give us 3t minus 3 ut minus 3, which is a shifting by 3 units. So x1t can be sketched to be look like this, yeah, which is a shifting of 3 units to the right. Okay, whereas for the yt will remains at itself, but the multiplication, yeah, because remember x to t is multiplication of x1t and yt. So when we multiply both functions, so that should be the results of x to t. We have yt, and this is x1t. So when we multiply these two functions, it can be then deduced that the value of t less than 3 will be 0. Yeah, less than 3, the value of the multiplication will be 0. So the value of multiplication will only exist for value of t bigger than 3. Yeah, because x1t, yeah, x1t here is 0 for all the value of t less than 3. So that is why when we multiply x1t and yt, the value of this multiplication for t less than 3 will be 0. Okay, so when we multiply x1t and yt for value of t less than more bigger than 3, we can then say that it will be this x1t multiply with a constant of 2. Yeah, we have a constant of 2 here for value of t bigger than 3 for yt. So the answer for this multiplication will be the x1t multiply with 2. So we're going to have 6. Yeah, 6 of 3 minus 3 ut minus 3. So that's multiplication value. Okay, so the Laplace transform for the x to t will be simply equals to 6 over s squared exponential of negative 3s, because we are using a shifting properties. Yeah. Okay, remember that x to t will be integrated to find the zt. Okay, so that is why in this step, what I did is I find the x2s first, because the zs can be calculated. Yeah, zs can be calculated by simply applying the integration properties. Remember the integration properties? Okay, so basically the zs will be simply x2s divided by s, because this is to be based on the properties of integration. So please refer back to the integration properties so that you can understand why we calculate the zs to be x2s over s. Okay, so we have obtained the x2s from the previous part. So that zs is simply x6 over s power of 3 exponential of negative 3s. Okay, so from here, we can find the zs, and further on, you can find the zt straight away. Yeah, so zt can be calculated, yeah? Because the question is to find the zt, sorry, is to find the z, signal zt in the s domain. So that's a question. So means that to find d is to find the zs, nah? Yeah, is to find the zs. So that should be the answer for the zs. Okay, so hopefully you are clear about these solutions. Okay, so for your information, these examples and these examples that we have here are these previous test 2 questions. Yeah. Okay, so that's the end of lecture 14. Okay, so hopefully you understand well on the topics of properties of Laplace transform. So next lecture, lecture 15, which will be the last lecture of chapter 4, we're going to learn about the application of Laplace transform, in which we're going to see how the Laplace transform is used in the solving the circuit analysis problem. Okay, right. Thank you very much. We are going to meet you next week for chapter 15. Yeah, so for lecture 15. Yeah. Okay. Thank you very much.